of Q arc beta, multiply Q arc beta. In the equation, we just EI minus rho mu this unit. And no.
P2S.
Here. And here is Q arc beta. Here is Q arc beta. I want to ask this one. This is the scalar or just the matrix? Because this is the tensor. This is tensor. Tensor is just 3 multiply 3 matrix.
I don't know. We have to ask them.
I mean, this energy is a scalar. When we calculate it, do we need to? This is the if this is the matrix. Do we need to just calculate this one? I mean, the fixed of this matrix.
We have two matrices there.
And this two matrix we can not multiply. Those products.
I don't know. Do we multiply them? I don't know what we do.
E is a scalar because if you see the subtitle, the symbol substrate is the same. You need to you need to have a summation. So there are two summation in this. So finally they will become a scalar. You need to summation beta at first, and then you summation the alpha.
Yeah. This is R and beta. This is the same substrate. And then if
Look, I mean,
this is
the really important thing are these subscripts, right? That tell you what happens. If all four are different, then you just have two matrices sitting there, no multiplication. Okay? If two of the subscripts are the same, then you multiply them together and you have a new matrix. If all four, if these two are the same and the other two are the same, then you multiply them first and then you take the trace. See, so what these subscripts are tell you exactly what happens. Okay? So first of all, having these alphas the same, if this were a gamma, this would mean you multiply the two matrices together. And then making the gamma equal to beta means you take the trace of the product. Okay? Okay. Any more questions? This stuff is, I mean, the tensor business will definitely be on the next level. This is okay, so I want to come back to just one more point here, that you plot the order parameter and the free energy density, and we have this nice picture, something like this. The free energy looks like this. And so if you're at high temperature, the lowest free energy is this, right? This is the lowest. And when you get to this point, the free energy is this. And there, the order parameter jumps from 0 to something. Okay? And now this is called a first order transition. Phase transitions are first order and second order. You could even have higher order, but this is called the first order transition. And there's a question as to how do you know what the order of the phase transition is. And there's a classification due to this guy Aaron Test, the famous physicist. And he said that the order of the phase transition is the, I don't know how to say this, is the order of derivative of the free energy with respect to temperature, lowest order, derivative of free energy with respect to temperature, which is discontinuous. Okay, so this is a nice definition because it tells you the answer, doesn't matter what the situation is. So let's have a look. Let's have a look here. So here's the free energy, and we are on this branch and on this branch. And so as we go through the phase transition, the free energy itself is continuous. It's a continuous function. But the derivative, the first derivative, is not continuous. Here the slope is 0, 0, 0, 0, 0, boom, something else. Right? So first derivative is discontinuous, first order transition. Now there are other situations which are not like this. So for example, there are systems where the order parameter looks like this. Well, you get the idea, it's symmetric here. It would look like this. So it's symmetric up and down. And if you were to plot the free energy here, you would find again that you have a solution like that. But in this case, the other branch would be like a parabola coming down. Okay? Where the slope of this branch would be 0. So this is the same kind of a picture. We have two solutions. Order parameter is 0 here. Order parameter is not 0 here. This is one free energy branch. This is the other branch. And this is exactly a parabola which kisses the line at this point. And so here, the first derivative is continuous. But the second derivative, which is the curvature basically, jumps from 0 to some finite value medium. So this will be a second order transition because it is the second order derivative which jumps. And this transition, you know, in principle you could have phase transitions where it is the fifth derivative. There are not many of those, but in principle you can imagine. So formally, that's the way to decide. You have to plot the free energy as a function of temperature and look to see which derivative jumps when you cross a phase transition. Okay, so just a nice thing to know. Practically, whenever you have a discontinuous jump in your order parameter, the transition will be first order. Here, the order parameter goes continuously from 0 to some non-zero value. It doesn't jump. It's second order. But formally, this is what you need to look at. Okay, everybody happy with this? And now, finally, I want to say a few words about how to actually do the homework.
I have checked what's the WRT. With respect to.
Oh yeah.
With respect to.
to.
It means you're plotting f as a function of t.
You know, saying take the derivative with respect to the variable t. Yeah, this is bad. I assume that everybody knows this, but it's good that you ask. I still remember when I was a student, an undergrad, I went to hear some talk, and some guy was talking about some material, and he was talking about dimensional stability. And I'm thinking, dimensional stability, material goes from 3 dimensions to 4, I have no idea. And all the guy meant was that it doesn't change its size, you know. It doesn't get bigger or smaller. So for him, dimension just meant size, you know. But if you don't understand some fundamental thing, then you can really get confused. So it's really good to ask if you don't understand. Okay, so homework. So the point is that you have to solve this self-consistent equation. 2USP2 KT. Now let's write out P2, okay? And we can change the variable to x, right? You can all do that. So the P2 just becomes 1/2 3x squared. Right? And then there's a -1 here. But that doesn't depend on x, so you can kind of pull it out. And the same thing happens in the denominator. So the term that comes out of here comes out of there. You can just cancel. So basically, we'll just get a 3/2 here. And rho u s 3/2 x squared over 18 dx. So, whoops. 1/2 3x squared minus 1. Yeah, that guy stays there. Okay. Everybody happy so far? It's all good? Change variables and we get rid of this multiplicative term because it's the same. You know how to solve this thing, right? You need to do an integral. So somehow you have to do an integral. But, okay, every piece of software knows how to do integrals, mathematical, no problem. But the issue is that you have an unknown in here, right? And how do you solve it? How do you solve it? Now, you can think of this problem as a kind of a root finding problem. So, for example, you can think of this as s equals some function of s. Right? So that would be kind of like so this is s, and I plot this function of s for some value of this parameter here. I'll get something. I don't know what. Okay? And then if s were to be equal to that, then I also have to plot s here, and I have to look at the intersection of these. So this is a standard problem of finding the root. S equals f of s. And there are techniques for doing that. And one way to solve this problem is to use one of these root finding techniques. There's Newton's method, for example. There are just different ways, bisection method, there's lots of different methods. But I think that there is a simpler and a nicer way to do it. And the idea is this. First you ask yourself, what do we want to find here? Well, we would like to have a graph of S as a function of temperature. Okay, so temperature is here, but we have this other stuff here, rho u over K. So, now one of the units of rho u over k. Temperature. So this is some kind of a quantity with units of temperature, right? So we can just think that this T divided by this thing is some dimensionless temperature, basically. Right? So we can write that little t be big T divided by rho u. Yeah, it's kT over rho u. So now we can replace this just by little t. So that's another point that we were mentioning, that in a computer, you cannot have quantities with units. Computer can only deal with numbers. Right? It cannot represent length or anything else, right? Just numbers. So before you do anything in a computer, you need to write things in dimensionless form. And it's important to do that, and it's important, sometimes people do sort of automatically. It's important to think about what you are doing. This process of making the problem dimensionless before you do it numerically often gives you insight about what the relevant quantities are. So that's a good thing to do. Okay, having done this, our problem is dimensionless. T has no units, X has no units, S has no units. Okay. Now, so what we want is basically we want a graph of S versus little t. That's something. All right. And so one way to do it would be to try to find, choose a value of t, choose a value of little t, then go through this root finding scheme to find the corresponding x, and then just do it again and again and again. Okay, but a nicer way, in my opinion, is to do the following, is to say, okay, let's do it this way. Let's call this quantity here, this whole thing in here, let's call it gamma. Call S over T, T halves gamma. So in general, gamma is going to be some number. So a kind of a nice trick to do is to say, okay, let me start with gamma, choose gamma. I just choose a gamma. I'll just say gamma is 4. Okay. I choose a gamma. Once I have chosen gamma, I can calculate S. No more unknowns, right? I just put in the gamma, I calculate S. Once I have S, I can come back here and get T. Once I have S, calculate T. So in this way, I don't have to do the root finding. I just choose gamma, and then for that gamma, I find what S and T are. And I just keep on doing it until I get a whole bunch of S and T and apply. Okay, so that's a lot more efficient than doing this root finding. I mean, the problem is that you don't know a priori what T will end up being. But you don't care, you just want to plot a graph. So, okay. Then you can ask yourself, all right.
Sorry, but then if gamma is constant, well, it will be constant every time, right? So if we plot some dependence of S on T, we'll get linear dependence every time.
No, you're saying change gamma. You change gamma every time.
Absolutely not. For you choose a gamma,
Yes.
and you get a corresponding S and T.
How do I choose S or T?
You don't choose it.
S is
You choose gamma, then you calculate S. Then you come back here, and you stick gamma in here, do this integral, stick gamma in here, do this integral, take the ratio, and you get an S.
Oh.
Now you know what S is. You have
So in the beginning, we know the temperature.
no.
What means no? We
Nothing.
do.
Nothing is no.
So if we do not know S and we do not know T, we
Right.
have only gamma. And if we have only gamma, we say that S and T are proportional.
No.
So
Yes.
we get S
So that
from
means-
gamma.
But to get S from gamma, we need T.
No, that's
Where?
here. You've already chosen gamma. It's 5.
Yes.
You've calculated S. It's 0.3. It gives you T. The point is, if you do the calculation properly,
Oh,
You
I
choose-
see. Yes. Yes.
all right. So they just saves a lot of work for you.
Yeah.
So
I
that's
got
it.
the moment of numerical calculations.
So you go through these gammas and then you get S and T, and of course, you then need to calculate the free energy also, right? But once you have S and T, then you calculate that, right? Okay, so then the only question is, what should gamma be, kind of? Well, you can sort of figure out what happens now. You know, if the temperature is high enough, the thing is going to be isotropic, so you don't need to go to a very high temperature, right? Now, we said that this is about, we said that rho u over kT was about, yeah, so this would be something like, 0.4 or so. So okay, so let T go up to 0.5 or 0.6. Start. Obviously, if S is going to be 0, gamma will be 0. So you want to go down to 0. But wait, S can be negative, right? S can be negative. So you want gamma to be negative as well. How negative? I don't know. Go down as far as you want. -2, -5. Yes.
It seems like we should be getting more than one S though for a given gamma where you would have more than one S.
But it's true that if you dial in a T, I mean, if you do the problem with this root finding, yeah, you will find more than one S. But on the other hand, even though at one temperature there may be 3 different values of S, there will be 3 different types of gamma.
So you're saying that
At one temperature, for every S, you must have a different gamma. So there's a one-to-one between S and gamma. And when you do this, what you will find is that as you cycle through the gamma, say from 0.5 to -3 or something, okay, this is monotonic, right? And S will be monotonic, but the temperature will not be monotonic.
okay. So you will get.
So you think of the multiple solutions,
Okay.
just the same. Okay? So I think that's a nice way to do it. Now, any questions on this? But I want you to, like I said, Miyasato theory is really a kind of a cornerstone thing. I want you to do this calculation really well, accurately, don't fool around with, 3-figure accuracy or something. We want to know things dead on. We want to know exactly where those temperatures are when you have the transition of everything else. Okay. And when you do this, you will find, for example, that as there will be a region where S is going to be increased, S is going to be decreasing and decreasing again. So suppose you're at this point of the curve, right at the very tip. Then you'll find that the temperature here is going to be increasing, so temperature is going up, it will stop, and then it will go the other way. That's what you find, right? Because when you're down here, temperature will be the same as what it is when you're up there. So when you see this kind of behavior, you want to take small steps in here. So you get these points exactly right. You just take a couple of points here, you're going to miss that altogether. So really do it carefully and do it in such a way that you can adjust your step size depending on where you want to look carefully. Okay.
What about the zero solution? Does that come out of this too?
Yeah, the zero solution happens when S is equal to 0, gamma is equal to 0.
So T can be anywhere.
Okay, and then T would be anything.
Right. Yeah, I mean, you won't, you won't get a whole bunch of T values out of this.
Right.
Implicitly. All right. Okay, so everybody's happy with the homework stuff. Okay, so this is the end of my Osaka theory. After this, we'll move on to other things. Now, Friday is midterm. I'll try to get another room for you so we won't have to move during the midterm. I'll send you an email about that. And this evening then, I guess you will meet with these folks to discuss things. And if you need me, I will be around. Yes?
Shall we have the midterm on the same time as we usually have a class?
Yes. Do you have another suggestion?
No. I'm totally happy about that. I'm absolutely happy about
I mean,
that.
if you want to start earlier, we can do it. I mean, I'm pretty flexible. So.
If we start a little earlier, in this we can have more time in the weekend.
No, the length of time will be the same.
Yesterday the weekend is too early for us.
No, the length of time is the same, but if you want to start earlier, half an hour earlier, we can do that.
Well, I don't really like that
Okay.
option.
All right, we start at 11 sharp. Make sure that you bring a calculator. You need to calculate something. And no notes. I will give you all the information that you will need. So all you need is paper, pencil. I'll give you paper too. But make sure you bring a calculator.
Can I use a mobile phone instead of a calculator?
Yeah, so long as you don't call some expert.